We're going to talk about work and energy. Let's use our first example here, because the best part about having that nice open discussion where you took a bunch of notes about what work and energy is like is that eventually I have to ruin it all by putting math to it. But the best part about ruining it all with some math is that math is a certain amount of absolutes. So once we start looking at the math of it, we have to find a way of expressing all those things we just talked about, but using math. So there's me pulling on the chair, right? I applied a force to the chair, and you guys helped me understand that there was also a downward force due to gravity and an upward force due to the normal force. And I'm not doing a great job making these look great, but I'm just trying to get us an idea. And a frictional force that acted on the chair as well, it acted at the ground. So let's put it closer to the ground. There we go. All right, so all these forces are acting on the chair. As I said earlier, we're talking about work. It required that the chair change its position. So the chair started over here, and through the actions of these three forces, it ended up changing its position. Right, it moved to the right. If I was to label these, I'd have tension, normal, weight, and friction. For the first couple of days of doing work problems and dealing with energy, I'm going to write out the word work so that we don't confuse it with the W for weight. Does everybody understand? Because technically the symbol that we use for work is just a big capital W. Nothing special about it, and we've been using capital W for the weight. So I will write out the word work whenever we're calculating work. To talk about work, we have to talk about the individual force that causes the work to be done. So I think we all can agree that there's going to be force in this relationship. And as you can probably imagine, there's going to have to be something in this relationship about the displacement as well. If I move the object further, I am probably doing more work. So we are going to have something about the displacement. Now, continuing this idea though, work is only done by a force that has a component in the direction of motion. So the direction of motion is itself a vector. Now, it's not a force vector, so I'm drawing it in blue because it's not part of a free body diagram, but this is the direction of the displacement. So when we talk about work, and we talk about it being done by a force, we need to compare the direction of the force with the direction of motion. So when given angles in any force problem, if you're asked to talk about the change in energy or the work being done, any angle needs to be converted in such a way that it represents a comparison with the displacement. So if I gave the direction of the tension relative to the vertical, you'd have to change that angle to be related to the displacement. Now, if I wanted to figure out how much of my force is in the direction of motion, which trig function would likely give me my answer? Cosine, yeah. It's going to have to be the cosine of the angle. Right, that would give me the little part that I need. Now, we have a special notation for this. In mathematics, we call the product of two vectors that leads to a scalar the dot product. And it looks like that, a big dot, the dot product. Sometimes called the scalar product. It takes two vectors and produces a scalar. However, it's a special kind of multiplication. The dot product tells you to multiply the two vectors, but the first vector, only the part that's in the direction of the second vector gets multiplied together. That's what the dot product means. It's the product of two vectors in the direction of the second vector. So it's looking for you to take and find the angle between the two vectors and multiply by the cosine of that angle. That's what the dot product means. There are other kinds of vector products. In fact, another one we'll talk about later is called the cross product. The cross product produces a vector. It wants to find out how how much of one vector is perpendicular to another. But this is trying to find out how much one vector is aligned with another. So that's what the dot product does. But it produces a scalar answer. So work is a scalar. It can be positive or negative, but it doesn't have direction. In fact, energy is a scalar. It can be positive or negative, but doesn't have a direction. Now, we don't talk much about negative energy. We will, but we don't talk much about it. It's nothing special. Negative energy generally deals with reference. But kinetic energy can't be negative because it's all about motion. It can be zero, but it can't be negative. Now, looking at this is all just notation. But there are some things here I think that are important. Let's apply this formula to what we just talked about. Look at the normal force. From this formula, would the normal force do work? Why? But what's another part mathematically that says it here? What is the angle between the normal force and the displacement? 90 degrees. And what is the cosine of 90 degrees? 0. So this formula automatically negates the normal force as doing work because of the angle. Can we say the same thing about the weight? Now, what is the angle between friction and the displacement? 180 degrees. What is the cosine of 180 degrees? -1. The angle determines whether the work being done is going to be positive or negative. So obviously angles less than 90 do positive work. Angles greater than 90 do negative work. And angles that are 90 do 0 work. Fair enough? All right. This will be our definition of work, and there's more to it. We are assuming two things here with this definition that we will not be able to assume for very long. We are assuming that the force is a constant, the displacement is a constant, and the angle is a constant. Now, the displacement is going to be a value, but we are assuming that the force and the angle of that force are the same throughout the entire displacement. That's what this assumes. In fact, you should write somewhere on here that this formula assumes the force and the angle of that force are a constant during the displacement. But that's obviously a very specific case, which means we will have to be working towards a situation in which the force can be changing over the course of the displacement. Now, if that's the case, what we have to do is consider what the force was over a very small displacement. A small displacement changes your delta to a lowercase d, saying we're taking a look at what that force was for a portion of the displacement. So if I move the chair from one end of the room to the other, we're talking about 1 centimeter's worth of the displacement. What was the force during that centimeter? And then adding up the force during the next centimeter, and then adding up the force during the next centimeter, and doing that from one end of the room to the other. Now, there's a math way to write that we're going to add up all of the different displacements. That will be an integral. Yes, very good. So we are going to have to work towards a situation in which the force is changing over the displacement. That's not going to be right away because you guys are not here yet. We will spend a lot of our time here, but we will have to redress this for situations where this is true. That is our future. One final little thing. Units are newtons times meters. That order is important because a meter newton is something else. So Newton meter. And we have given this the name joule. So although you learned about joules in your chemistry class, it has much better context here because it's based on force and displacement. That is a kilogram meter squared per second squared.
That makes sense.
Well, it does if you know the definition of kinetic energy. All right.